So welcome back to the class Neural Dynamics. This mathematical detour lecture is about the problem of separation of timescales. Those who have had no problem with the quiz of part 1 of week 4 can skip this lecture and go immediately to the next lecture. For the others, I have added here some details that may help you to understand the notion of separation of timescales. The assumption is that we have two coupled differential equations, and the timescales of these differential equations are tau 1 and tau 2 respectively. And the assumption is that one of the two variables is much faster, or tau 1 is much faster than tau 2. So let's look at an example. We start off with a single linear differential equation characterized by a timescale tau 1. X likes to go towards C. C is a constant, but the value of the constant may change. So you may think of this as some kind of input. First it has a constant value, say C1, and at some point it changes to a new value, C2. Then we know that X will approach the value C with some time constant tau 1. So suppose it was already at equilibrium. So I plot here X was at equilibrium. At this point here, we have the change, and X will follow and approach the new value, C2, exponentially with some time constant tau 1. Now suppose tau 1 is short. That means it sort of goes very quickly up to the new value. Now if I don't look at a very fine timescale, but if I sort of step back a little bit and I look at some steps, then it looks as if the variable x has jumped. It has responded immediately. Here it was still below, and now suddenly it's up here. So x approaches the value c of t rapidly. Rapidly means with a time constant tau 1, but tau 1 is short. Now, if I look more closely, if I increase my resolution, I would always find that, well, indeed, there's this phase of exponential approach. And the reason is that a step signal is a signal that makes a rapid change. Now let's consider a situation where the change is slower. Suppose that at this point here, my signal, c of t, which drives my differential equation, changes to some new value. Or it might continue to change all the time. Now at each moment of time, x will approach the present value c of t, but it takes some time tau. However, if the time constant tau 1 is short, then it will sort of approach immediately its value. And it will copy the momentary value c of t. There's a tiny, tiny little delay between the two, but it's not visible. So it's a very good approximation that x is equal to its target value c of t. In fact, this becomes true in the limit that tau 1 goes to 0. Then x will immediately take its new value c of t. So far for a single differential equation. Now let's look at a system of coupled differential equations. I assume that the time constant of the x variable, tau 1, is much shorter than the time constant tau 2. Now here I have an external input, which for example may be switched on at some time to some new value I0. Now the variable C is low-pass filtered. It responds slowly to the change in the input. So C itself will approach its new value I0 with a time constant tau 2. So that's basically the time scale here. That sets tau 2. Now we have assumed that tau 1 is much smaller than tau 2. Now from the perspective of the variable x, we now have exactly the situation that we discussed before. We have a slowly changing target value c of t. Therefore, the variable x will just follow its target value c of t. Why is that? The reason is that tau 1 is much smaller than tau 2. So the fact that the variable c is given by a differential equation means that c is slower than a potential external drive. C of t is guaranteed to react slowly because its dynamics are characterized by the time constant tau 2, which is slow. Okay, so these are coupled differential equations, but the coupling is one way. Let's now generalize this. So I might still have some kind of input which controls my variable c, but then c also gets input from x via this function f of x. Moreover, as before, c enters the x equation. We make the assumption that tau 1 is much smaller than tau 2. Now there could be a fast drive here, like a step current as before. There can also be a fast drive coming from above. It doesn't really matter where the drive comes from, because whatever comes as a drive is low-pass filtered with this time constant tau 2. So this signal here will be slow. I don't know exactly what it is, but it will be slow. Now, since it's slow, x of t can follow. X will approach its target value c of t rapidly because tau 1 is much smaller than tau 2. Therefore, x will be some copy of c of t. I admit that my hand-drawn copy is not very nice, but I hope you get the idea. Now, this is exactly the kind of arguments we used for the Hodgkin-Huxley model. We have an m variable, and this m variable is characterized by a time constant, a voltage-dependent time constant, and this tau m is much smaller than the other tau h or tau n. So we have a fast variable. M is the fast variable, and it's fast compared to what? Well, it's fast compared to the external. It's fast compared to the dynamics of the other two gating variables. Tau h is slower, tau n is slower, but it must also be fast compared to the stimulus. the stimulus should not be too fast in this case, so that we can say m follows immediately the voltage. M approaches m0 of u if the voltage is slow, which is the case if the stimulus is not too fast and the other variables cannot be fast because they are controlled by slower time constants. So m will approach m0 of u rapidly, fast compared to the voltage, and that's why we can replace m by its instantaneous value m0 of u. Now this works for all sorts of coupled differential equations. Whenever you observe a difference in time scale, you can exploit this difference and you can eliminate the fast variable. Now, before you go on, please check that you understood what I said by looking at the quiz questions now.